I think we can start. So it's my big pleasure to welcome here Professor Dr. Ruizhi Dong from Tongji University, from group of Professor Yang Li. And today we'll hear some recent results of the group in the field of topological acoustics. And the first question from the first slide, let me ask you immediately why they are preliminary. Yes, let's start with this.
It's not just everyone's preliminary. It's just our team and my preliminary exploration of the topological acoustic. Because I just do this kind of since about 15 years. So I think it's a preliminary exploration of the topological acoustic. So.
Okay, thank you for answering, and sorry for this abrupt, not very smooth start. So please, stage is yours.
Okay. Hello everyone. I'm Ruizhi Dong from the Tongji University. I'm really glad to be here at this seminar. And so here is my CV. My research interest is lying in the acoustic topology and noise control. As we all know, the topological has a really long history going all the way back to the Euro 7 bridge problems in the Königsberg, or in now we call it Kaliningrad, right? Up till this centuries, when the Tolles and the Hodan and the Costless win the Nobel Prize, and the topological physics has always been the hot topics in the physics research. So my talk comes cover everything about the acoustic technology and the topological acoustics. So if any research are interested in the related stuff, you can check out these review papers. They are all really solid and solid and strong work, and may offer you a great reference or guidance. All right. So let's back to the early research. The acoustic analog of the SSH mode was a really hot topic in that time. The SSH mode, as we say, sorry, let me use the light here. Like we see, is a one-dimensional chair-like structure, and each unit have two atoms and connected by the intracellular coupling and the intercellular coupling. So by control or by adjusting the coupling strengths, we can achieve the two topological phase transition. We can move the system to the travel from non-travel, or from travel to non-travel. Yeah. And if we after the chapter about the topological system, it can be see the localized phenomena occurred at the edge position of the system. In our acoustic analog, the cavity are usually used to represent the atom, and the tube, the connector tube, usually to represent the coupling.
Okay. So, Dr. Bob, may I ask you a simple question?
Okay.
So let's say you have this SSH array, you have an H state. So how do you map the distribution of acoustic field in the system? Do you insert microphones in each cavity or just in some of the cavities? So could you comment a bit on that?
Sorry, can you repeat your problem?
Okay. So do you insert microphones in each of the cavities to map the distribution of the field? Or you just map acoustic field in several points, in several cavities?
Let me.
In here?
Yeah.
Oh, yeah.
A lot of holes.
The microphone is used to measure the sound pressure levels response in the cavities, and the sound, as we say, is in here.
So these extra holes in your resonators, do they deteriorate the quality factor? So how sensitive is the quality factor to the insertion of these microphones?
About the microphone sensitivity?
No. How about quality factor? Because when you insert a microphone, you drill a hole, right? And because of a hole, your quality factor sort of decreases.
What you ask is about the hole and how.
Yes, and then what happens with the quality factor?
So I think the question is, like, do you put microphones inside each cavity?
This work is Wen Jiawei's job. It's not my work. But I think he really put the microphone inside the cavity to get the sound pressure level. Yeah.
So the question is, does it disturb the cavity? So when you put microphone inside the cavity, does it change the field, the microphone by itself?
I think maybe not. I think maybe not. Because the microphone's size is pretty smaller than the cavity. I just think, yeah. I don't think it will
Explain this a little bit more.
The acoustic mode. Yeah.
Yes, actually, you can just put the microphone not inside. It's just the boundary of the wall to avoid a lot of influence. Yes.
Many thanks. Now it's clear.
Okay, Ruizhi, you can continue.
Shall we go on?
Yeah.
Okay. And besides this SSH mode, the two-dimensional topological transport is also a highly significant part of the topological acoustic. Like in this work by the Nanjing University's Liang Bin's team, they report acoustic chain insulator, and they use the airflow bias to akin to the electronical quantum Hall effect to build a one-way sound transport along the edge. And besides this work, they can use the way not to break in the time reversal symmetry to achieve the topological transformation such as this work in the left by the He Cheng in the Nanjing University. He adjusts the cylinders in the lattice to open and close the double Dirac point. But in my opinion, it's fourthly degenerate point to create the topological phase transition. Yeah, and in the right side is Jiuyang Lu's work about the edge rotation of the triangle to achieve the crossway and anti-crossway energy energy fluent in the topological system to build one-way transport back to our research on the topology system. As we can see, topological system or topological state also realize a large and a higher dimension system to manufacture the smaller or in lead in a small rings localized nature. It means if I want to build a topological transport, I need use a lot of useless lattice in the device. It may raise the cost to build the device. So in our study, we entered two types of domain wall into the traditional quantum Hall effect acoustic topology system to build three layers structure to achieve the topological waveguide transport and let many as we can see the green sorry, as we can see in the
Dr. Dong, may I ask you also a short question one? So
okay.
When you talk about one-way propagation, so do you actually measure these S12, S21 coefficients as they do in electromagnetism? So how do you confirm that your waves propagate without reflections? By S-parameter measurement or
how? About here?
Yes, for instance here.
These two works is caused by the two different physics. The left one is acoustic quantum spin Hall effect. They use the cylinder, right? Like you can see the cylinder in the lattice. They adjust the size of the cylinder to achieve the energy fluence in the lattice and to let the acoustic transport along the edge. Here is system A, and here is system B.
Sorry for interrupting you, Dr. Dong. So I more or less understand the principle. I'm interested in the measurements which they actually do, because as I understand, you have a lot of losses in these acoustic cavities. So what kind of experimental result confirms that you indeed have one-way transmission? So do you measure simultaneous reflection and transmission coefficients as a function of frequency? How people do this in acoustics?
Yeah. I know you mentioned the loss in the test, right? Although he says he can achieve 100% dig output, but in his exam, it's just about 10% or maybe lower output. Yeah.
But how about the one-way feature? You said that this is a one-way transportation, but did they consider to use the revised from A to B, it is propagative, and from B to A is forbidden. So can they
like we see the project band structure, you can see there are two edge. The slope is positive and negative, so it means it can be transported from A to B and B to A, not like this one. It can only from A to B, not B to A.
Yes, I see. But did they measure in the experiment? Did they measure and to confirm this one-way feature? The principle is very clear because you have a momentum knocking in this structure, right?
Yeah.
But did the experiment to confirm this is totally one-way propagating system?
I think they didn't mention this.
Okay, they just show that from A to B it's propagative.
对。
Okay,
yeah.
I see.
And shall we move on?
You can go on. Okay.
And in this part, we show verification of the no reciprocal transmission and robustness like we can see, because we break in the time reversal symmetry. So in the topological waveguide, in the topological waveguide, we can achieve like we say A to B, and we can achieve the sound count from B to A, right? And about the robustness, we offset the airflow, the airflow from about this side, and it can be seen there always been a topological HD in the back. And
so here you said that from A to B it's allowed and B to A is not allowed, right?
You asked me?
Yes, from A to B is for A to B it's okay, but B to A is
yes,
totally
according to the breaking of the time reversal symmetry, yes, it's true.
Okay, I see. Thank you.
And like we see, the robustness according to the it's a 3-point structure. In a wide range of the flow velocities, it can mention the non-receptive calculation about the flow. Yeah. And in addition, we also can achieve the bin splitter and the multi-channel transmission communications. Yes, by this system. And as to next, we'll introduce our second piece of work, which focuses on the topological BICs. In other words, the topological BICs refer to the topological HD within the embedded within the backband of the other decoupled mode. Recently, there also have many excellent work about the topological BIC, such as Cho's research about realizing topological BIC through a simple and universal minimal striking and the Zhongming Gu's topological kernels they merge in the continue, right? Unlike their study, in our study, we have a construct based on the universal symmetry and observed that the TBIC really exhibited two characteristic, both the BIC sensitivities and the topological systems robustic to the disorder. So let's talk about our construction methods. We use the waveguide mode and the cavity mode. In this later, we call the sigma mode and pi mode to build a decoupled Hilbert space and achieve the topological system by adjust the d between the two cavities to adjust the intersealed and the intrasealed coupling to achieve the topological phase transition.
I'm sorry.
Okay.
Can you turn on the previous slide? So, how do you differ pi modes and sigma nodes? Sigma modes. I'm sorry.
Yes, you can see the right hand, this mode, the blue one. Yeah, you can see. This is the waveguide mode. It can be transported in the waveguide, but this kind of mode, we call it cavity mode or pi mode. It's in other words, it's a BIC in the waveguide continue, which means its symmetry is decoupled from the
waveguide, right?
The waveguide mode, right?
I see. Okay.
Okay.
So, Dr. Dong, I have also a question at this stage. So, do I get it right that you have a system, basically a waveguide, and there are multiple resonators attached to it? So, in some regimes, the waveguide mode could dominate over the oscillations in the individual resonators. In some situations, the oscillations inside the resonators dominate. So, as seen from those profiles. So, do I get it right, or? Few words about the system you are studying, how it's actually assembled.
The fundamental units you used.
Yes.
The pipe system.
I can't get your point. Sorry,
Do you have the fundamental units of the pipe? Actually, it's here. I will explain it a little bit. Actually, it's a two-sized pipe. The first one is this size, and the larger one. So we used two different color, and in this way we used actually it's two fundamental units. It's a supercell, but in this case we changed the supercell larger. The width is larger.
Okay.
So the second one, the width is smaller.
Okay.
Actually, it's totally the same. Just increase the topological phase inside.
Okay.
So in this way, we can have have a H state. Adjacent.
Yeah. I get your point. You're talking about how to build the topological phase. It's about the distance between the cavity. If we large or smaller the distance, we can achieve the topological phase change. Like you see these two pictures. Here is a large distance, and here is a smaller distance. Yeah. And
yeah, not clear.
And we'll move on. As we see, the energy band of the supercell, it can be observed that the sigma modes H state are embedded in the pi modes spark band, and we call this one we call this one topological BIC, right? And by adjusting the parameter of the cavities, and we can also achieve the envelope evolution of the topological state, like topological BIC and the topological final renaissance, and the traditional topological H state. Yeah. And as for its BIC's characteristic, when we appeared the axial perturbations in the system, it will remain robust to the disordered. And if we appeared the lateral perturbations, it will appear behavior like the BIC's experience splitter behaviors like the BIC's, right? And finally we verified these results, and like we see when lateral perturbations is applied, it's a splitter wide occurrence linears within the perturbation strength. It appears like a high sensitivities of the BIC like state. When under the axial perturbations, its behavior like the higher robustness of the topological H state. So this is our two works, and final, I'd like to express my gratitude to Professor Yongli, Xu Wang, and Dongxin Mao. And I don't know my pronunciation is right or wrong, but спасибо. Thank you.
Thank you very much, Dr. Dong. Any other questions from the audience?
Yeah, so I have one more question left. So in this band-binding description which you are writing, you introduce complex couplings. So do I get it right that these complex couplings actually describe the effect of losses in these narrow channels coupling the cavities?
It's about page where I should back to my PowerPoint.
A bit back. So you have complex couplings in your Hamiltonian, right?
Almost the first or second slides. The first one, I think. Yeah, the first one.
Here?
No. Here. You mean the V and the W?
At a bit later stages, he was showing that the couplings are actually complex. So I guess this is to accommodate the effect of losses. So it dominates over complex corrections to the eigenfrequencies. So what's the situation in acoustics?
Yes, of course. But as I last time we discussed, people don't want to consider these losses inside. They just said that this is the real coupling inside, and of course it will cost as shown in the literatures. They claim that the transmission is 100% transmission, but the energy we can measure is just less than 10.
Yeah, but that's an interesting feature because in electromagnetism we normally have a lot of complex corrections to the eigenfrequencies, so a lot of losses inside, but the couplings are okay. So here quite the opposite, if I get it right. So maybe the quality factor of resonators is more or less good, but we have a lot of losses at the coupling.
Yes, but coupling is a degree of freedom we can tune, right?
Yeah, sure. Okay, good. That's interesting. Thank you.
Yes, and in acoustic, it's very easy to tune the loss. We can tune the width of the pipe.
Yes, as you mentioned. So another question: do you have a capability to tune either the coupling or the eigenfrequency of the resonator in real time? So creating effectively time-modulated structures, which I was curious about.
Yes. Ruizhi, you can reply. The time varying system.
Yes, sir, please.
The system is varied with time.
The frequency acoustic, frequent acoustic, right?
No, like can you change the parameters of the resonator in time?
In time, yes.
Like vary frequency in time, vary coupling in time.
Yes, I know. I know this kind of topology called a frequent topological. But I'm not know too much about this kind of field.
Actually, there's very little literature on this. Yes.
But technically it can be done.
Yes, technically it can be done.
That's very
yes.
Maxim, this is one of the aims of our project.
Yes, it's one of the.
That's perfect. I mean, there is a lot of problems there. Interesting ones.
Okay, if any other questions from the audience? Maybe another technical question from me. So what about the material of so you use plastics or what?
Sure.
For the material, plastics is okay. It has because we usually use the sound about 3000 hertz, so plastics is do not influence do not cause the sound link from the cavity. Yes, plastics okay.
I see. I got it.
I think all the solid materials are fine because the impedance between between air and solid is extremely huge. So we just use some materials that is used for normal 3D printing technology.
I see.
And the glass and the steel is all fine. It's all fine. Yeah.
All right. Any other questions? Okay. If not, I think we can end this with this. So thank you very much. Thanks much, Dr. Dong. So I think it was very interesting and illustrative, and we hope for future collaboration, right, in this direction.
Okay, thank you. So I stop my sharing the screen. Okay.
Yeah, thank you.
Thank you.
So let's thank the speaker once again.
Thank you everyone. Thank you everyone.